we are going to focus now on transformations that go from Rn to Rn. And we are going to define the important concept of eigenvector. An eigenvector is a vector in Rn, in the domain of the function, such that when it's transformed by the function, gets transformed in a multiple of it. If the vector is like this, the transformed have to be like this, or like this, or like this. Any vector that is a multiple of the vector given. So if we have a vector that when we transform it, if this is B, and when we transform it, we get something like this, so this vector is not going to be an eigenvector. Instead, a vector U, that when we transform it becomes in something like this is going to be an eigenvector. Okay, so an eigenvector then is a vector in the domain such that when we transform it, we obtain a multiple of it. Very important, this vector cannot be zero. So an eigenvector is never a vector zero. So the definition of eigenvector is any vector whose transformed is multiple of it, but is not zero. And traditionally this multiple, if it's 3 times the vector, or 4 times, or 1/2, this scalar here traditionally is called lambda. It's used this letter for the eigenvalue. So the eigenvalue is going to be that number that determines what multiple of the vector is. So if we have that there is a vector that when we transform it becomes a multiple of itself, and this vector is not zero, so this vector is going to be an eigenvector, and this number here is going to be called eigenvalue. And we are going to say that this is the eigenvalue associated to this particular eigenvector. So, for instance, let's say that we have this transformation. This is a transformation that goes from R2 to R2, right? So this goes from R2 to R2 and transform the vectors in this fashion. So let's ask, for instance, if this particular vector, let's say this vector 1 minus 2, this is a vector in the domain, right? Just a vector 1 minus 2. So the question is this vector an eigenvector? And so, to answer that, we will need to transform it and see if the transform vector is really a multiple of it or not. So, let's transform it. So, let's do t of 1 minus 2. Let's follow the transformation. This is x minus y. X minus y, in this case, is 1 plus 2, which is 3. And the other one is 2x plus 4y. In this case will be 2 times 1, which is 2, plus 4 times minus 2. So that will be 2 minus 8, which is minus 6. Okay, so we find the transformed of 1 minus 2. So is this vector a multiple of this? Well, we see that in this case it is, right? Actually, this is 3 times 1 minus 2, right? 3 times 1 is 3, and this is 6. So it's really a multiple of this. We can see here that we put this vector here, and now we obtain 3 times this vector. So this is really a multiple of it. So then what we can say is that the answer is yes. So this is actually an eigenvector, and this number, the number 3, is actually an eigenvalue of this transformation. Equivalently, instead of the transformation, the formula of the transformation, we could have taken also the matrix associated, and this is more common when working with eigenvectors and eigenvalues to refer all the work to the actual matrix. So let me do it again with the matrices. So the matrix of this transformation, we put the coefficients of x, we can see that is here 1, 2, and now the coefficients of y, we can see that is minus 1, 4. So that's a quick way to calculate the associated matrix. And so an eigenvector will be a vector that I put here, such that the result that I obtain here is a multiple of it. So in the case we had calculated a moment ago with 1 minus 2, we do this operation with the matrix and we get 1 plus 2 is 3 and 2 minus 8 is minus 6. So we see again the same thing, right? So this 1 is 3 times this, so then this is an eigenvector. We can see also that there are vectors that are not eigenvectors. So let's put just this vector, for instance, 1, 3. Let's multiply. So when we multiply here, we obtain that this is 1 minus 3. This is minus 2. And the other one is 2 plus 12. This is 14. So we can see here that this vector actually is not multiple of this. This can be seen clearly, right? So because we see that in order for this to be a multiple, it should be multiplied by minus 2. And definitely 3 times minus 2 is not 14. So this one is not a multiple. So we can say that the vector 1, 3 actually is not an eigenvector. Okay, so that's the idea, what an vector and eigenvalue is. We can see also that these eigenvalues are obtained by writing this equation. Let's just use A now for the associated matrix. By writing this equation and see if we can find a solution here that is not 0. So we have here the equation A times B equal a multiple of B. Well, if this equation has a solution that is non-zero, so then that means that the vector V, that solution that is non-zero, is an eigenvector. And so we know when a system has or doesn't have solution 0 or non-zero. We can write this as a single one by putting everything in one side. We can say that this equation AB equal lambda B can be written as AB minus lambda B equal the vector 0. And we can take here V as a but in order to take V as a common factor, so lambda here cannot be left just as a number, so I need to multiply actually lambda by the identity matrix. So I have two matrices to subtract. So I can put here A minus lambda times the identity matrix B equals 0. So in that way, so this original equation that we have here, we can write it actually as this one, and this is a very important equation, is homogeneous, is equal to 0, so we know exactly when this system has a solution that is non-zero or not. Observe that the solution 0 always exists, right? Because if we have a matrix times V equals 0, of course if we put here 0, always exists. So we know that this system is compatible. So we know that the system has solution. At least the solution 0 is there. So the point here is not if it has solution or not, is knowing that it has solution if it has a unique solution or it has infinitely many solutions. And what we want is to have infinitely many solutions, because if it has a unique solution, means that the only solution here is 0. And we are not interested in the solution 0, right? So we know that an eigenvector is something that is not 0. So what we are interested in knowing is this system actually has infinitely many solutions. And we know that this is the same thing that's saying that the determinant of the system is 0. right? Because if the determinant is not zero, has a unique solution. I mean, only the zero solution. And so we want the determinant to be actually equal to zero to be guaranteed that this system doesn't have a unique solution, that the system has more solutions, so we are guaranteed a non-zero solution. Okay, well, this equation is very important, has a particular name, is called actually the characteristic equation. So this equation, the determinant of this matrix equals 0, this equation is what is called the characteristic equation. And the solutions, I mean the values of lambda that makes this equation true, the solutions of this equation are actually the eigenvalues. So we are going to say then the characteristic equation is, as I just said, the determinant equals 0, and just the determinant, just this part, is what is called the characteristic polynomial. So if you have the polynomial equal to 0, you have the equation. Otherwise, if you have just the expression, then it's called the characteristic polynomial. Both the characteristic polynomial and the characteristic equation and very important data of a matrix, since the eigenvalues are going to be the solutions of the characteristic equation. So, what's going to be the way then of finding the eigenvalues of a matrix? Well, first, we are going to actually find the characteristic equation. Then once that we have this equation, we have to solve it. I mean, find the values of lambda, and those are going to be the eigenvalues. Okay, so let's start finding the eigenvalues in a, let's do it with this particular transformation that we work at the beginning. At the beginning, I just gave you just a random vectors to check, but now let's calculate actually all the eigenvalues of this matrix. So we have that the matrix given was the matrix 1, minus 1, 2, 4. And so to find the eigenvalues, first we have to calculate the characteristic equation. So that means to calculate the matrix A minus lambda I, and then calculate the determinant of this. So essentially, to subtract lambda multiplied by the identity, I mean, imagine the identity, well, in 2 dimensions it's like this, right? But it's the same in any dimension. When we multiply the identity by lambda, what we are doing, because there are ones only in the diagonal, is just put lambdas in the diagonal, right? So and everywhere else is 0. I mean, lambda by the identity of any dimension that have zeros here is a matrix that is equal to lambda in the diagonal and have 0 everywhere else. So essentially, when we have to subtract lambda multiplied by the identity, essentially we have to just to subtract lambdas in the diagonal. So in this case, in this matrix, so we're going to just subtract lambdas in the diagonal. So that will be 1 minus lambda, minus 1, 2, and 4 minus lambda. And now we just calculate the determinant. In this case, it's a 2 by 2, very easy to calculate, right? This minus this. So let's calculate this. So that will be 1 minus lambda times 4 minus lambda minus 2 times minus 1, which is 2. Let's do the operations. So that will be 4 minus lambda minus 4 lambda, just doing here distributive, right? And so plus lambda squared plus 2. Let's combine like terms or order this polynomial, and this will be lambda squared minus 5 lambda, 4 and 2 is 6. So this so far is actually not the characteristic equation, but the characteristic polynomial, right? So what I'm calculating here, this is the characteristic polynomial. And now to get the characteristic equation, I have to write it, the characteristic equation, let's say. So that will be to write the characteristic polynomial equal to 0. And now I'm going to solve this characteristic equation. That means, well, just to solve the equation, right? So whatever it takes depending on what type of equation is. In this case, it's a quadratic equation. Then we can just solve this one by quadratic formula, right? So lambda will be equal 5 plus minus square root of, and so lambda will be equal 5 plus minus 1 over 2. So one of the roots is 5 and 1 is 6, over 2 is 3, and the other 5 minus 1 is 4, over 2 is 2. 3 and 2. Okay, so these are going to be our two roots. So one of the roots is 2, and the other one is 3. These are then the eigenvalues of this matrix. So let's write down that the eigenvalues are 2 and 3. These were the ones that we obtained. So what does it mean? That whatever eigenvectors we have, what we are going to obtain in this particular matrix is that when we multiply the matrix by the eigenvector, it's going to be equal to the double of the vector or the triple of the vector, because these are the only two eigenvalues that this matrix has. The eigenspace is a space a little bigger than the eigenvectors. Contain all the eigenvectors, but also contains the zero. So the eigenspace of A, corresponding to the particular eigenvalue lambda, is the set of vectors B such that AB is lambda B, with that particular lambda. In other words, putting again everything in one side, is the curve of this transformation, something that you already know how to calculate this space. So the curve of this transformation. All the vectors in this space, in the curve, are not eigenvectors because it's also they are the zero. But most of them are. So we are going to say that this space here is the space of all the eigenvectors plus the zero. To calculate the eigenvectors, we are going to need to calculate then these spaces. So we're going to have to calculate the curve of a matrix. So we are going to find this matrix that we have it already since we calculated the eigenvalues, and then we will calculate the curve of that matrix. So for instance, in the matrix that we have calculated before, when we calculated the eigenvalues, was 1 minus lambda, minus 1, 2, and 4 minus lambda. So this is the matrix then A minus lambda I. And so now we want to calculate the kernel of this matrix for the particular values of lambda that we have calculated. So we have calculated before, let's come back to where we calculated the eigenvalues. These were the eigenvalues 2 and 3. So we want to calculate this space for each of them. So for when lambda is equal to, for instance, so this matrix for this case is going to be equal to 1 minus 2 will be in this case, right? 1 minus 2, which is minus 1, and then minus 1, 2, and here 4 minus 2, which is 2. Okay, so this is the matrix then that we obtain by substituting here lambda by lambda equal 2. Okay, and now what we want now is to calculate the curve of this matrix. Is the set of vectors xy in R2, right, in the domain, such that when we do the transformation by this matrix, when we multiply this matrix by xy, we obtain 0, right? The vector 0. So that's the definition of curve, right? So all the vectors that when we transform them became the 0. Okay, and so by doing the operation here, we get that this is the set of xy such that, let's do the operation here, right? This by this is equal to minus x, let me put it as columns as is written there. So I got written as columns. I could say that this is minus x minus y and 2x plus 2y, right? So that's multiplying like this and multiplying like this. Okay, this vector had to be equal to 0, 0. And then this is the set of x, y, and here we put just equal to each other, right? The x, y such that minus x minus y is 0 and 2x plus 2y is 0. Well, this is a system of equations. We can do the reduced echelon here, and we can see that we obtain only one matrix. So just quickly doing the echelon of this matrix, this is minus 1, 2, 2. We just add these ones here and reduce. Here will be, 1, 1, 0, 0, for instance, will be one of the reduced forms here. Okay, so then we see that we have only one equation here, that is just x plus y equals 0, or just this one, which is completely equivalent. So we can say then here that the kernel is the set of xy such that minus x minus y equals 0, for instance. Just leave it like that. And here we can write this as a as parametrics, right? Remember that this is a system that have infinitely many solutions, so it will depend on a parameter. So let's call y equal t, for instance. So if we made this choice to call y equal t, so then solving for x here, we will have that x is equal minus y, so then x equal minus t. So these are the parametric equations of this space, of the kernel. So in particular, any of these vectors can be written. I mean, see that if we write this as a vector here, xy, that is the vector minus tt, actually, is the same thing if I take the parameter out, that minus 1, 1. So we can take the parameter out, and so we have here a base of the space. So we can say that the curve is then the space generated by minus 1, 1, or the base of the space is minus 1, 1. Or you can say just that the space is the space of the xy such that x equal minus t and y equal t. I mean, all are equivalent ways to calculate the kernel. And so, what about the eigenvectors? Well, anything here is going to be an eigenvector. So, in particular, we can already see that the eigenvectors are not unique, right? So we have many. So one, for instance, one particular eigenvector will be this one, minus 1, 1. That's one particular one. So I can say, just as it's a particular one, I can say that the vector minus 1, 1 is an eigenvector. That's one possibility. I can say that, but I can say many other things. No, I can say, for instance, that the vector 2 minus 2 is another eigenvector. I mean, I can multiply by any t I want, and I obtain any possible eigenvector. I could multiply by t here, right? Here is what is the small difference between the eigenspace and the eigenvectors. So if I multiply, I put t equals 0, so then this is part of the eigenspace, right? So the curve contains the 0, 0. So contains 0, 0, minus 1, 1, 2 minus 2. All those are elements in the eigenspace, but not all of them are eigenvectors. So the eigenvectors are all of them except 0, 0. So for instance, minus 1, 1 is an eigenvector, 2 minus 2 is another eigenvector, put t equal 25, and you will get minus 25, 25, another eigenvector. Okay? All these eigenvectors I'm mentioning are all associated to the eigenvalue lambda equal 2. So if you want to calculate for the other eigenvalue, you have to do it again. So let's calculate it for the eigenvalue lambda equals 3. So we come back to the same matrix and substitute lambda by 3. So the matrix in this case will be 1 minus 3, that's minus 2, minus 1, 2, and 4 minus 3, which is 1. So this is the matrix in this case. That again, we need to find out when this system that, what is the solution of this system. Okay, we can do the echelon of here, and we can obtain like minus 2, minus 1, 0, 0, right, by just adding these ones here. So this is the echelon matrix here. So we can see that the only equation that matters is minus 2x minus y equals 0. Here we get that y is equal minus 2x. And then by calling x equal t, we get that y is equal minus 2t. And so these are the equations that define this kernel, right? So in this case, we were calculating the kernel of a minus 3 identity. So this kernel is then given by this equation. So it's the set of xy such that x is equal t and y is equal minus 2t. Again, we can get this is the description of all the vectors in the kernel. So if we want to extract from their base, we can say xy is t, that comes as a common factor here, and so multiply by 1 minus 2. And so here 1 minus 2 then is one eigenvector that is the base of this space. We actually have seen directly at the beginning that this was an actual eigenvector associated to this eigenvalue, and that will give an idea also of a check of this. How do we check that this thing is correct? I mean, we are getting that this is an eigenvector corresponding to this eigenvalue. What would be a possible check that this thing is correct? Well, we just multiply this vector. We know what means to be an eigenvector and an eigenvalue, so we check that this thing is true. So let's take, if we are saying that 1 minus 2 is an eigenvector for the eigenvalue lambda equals 3, we know that this has a very concrete meaning. Means that when we multiply a by this vector, 1 minus 2, we should obtain 3 times 1 minus 2. So that's what means this. So what we can do is, in fact, we do have the transformation. What we can do is actually multiply, transform 1 minus 2 and check if this is the triple. And this is what we have done at the beginning, right? So we have that the matrix 1 minus 1, 2, 4, we actually did multiply by 1 minus 2. We did the multiplication here, and we obtained that this was 3 minus 6. So the check will be to say, well, okay, is this, the question will be, is this really equal to 3 times 1 minus 2? And it is, right? So you see 3 times 1 is 3, and 3 times minus 2 is minus 6.